In this video, we're going to do a few examples with optimization. So in the last video, we introduced optimization and talked about a process for doing it, that we want to first understand the problem, draw a picture, and think about what the variables are. We then want to write an equation describing what we're trying to maximize or minimize. We then find critical numbers using the first derivative and use that to find potential extreme values. So then we want to verify that the value does give the maximum or the minimum, whichever one you're looking for, using either the first or second derivative test. And finally, identify all relevant values asked for in the problem. So let's do an example. An open top box is made by cutting out square corners of a 12-inch by 12-inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? What will the volume of the box be? Pause, start to think about this problem, draw a picture to think about what this looks like, and we'll talk about it together in a moment. Okay, so let's first start by drawing this picture. So we've got this 12 by 12 inch sheet of tin. So it's 12 inches, and we're cutting out corners of the box. We're cutting out square corners, and then after we cut out those corners, we're going to fold up the corners of that box. I think this is how we made like Easter baskets when I was little. We're cutting that up, and then we're going to fold up the sides and weld it together or whatever. And so the question is, how large should these sides be to make the box hold as much as possible? So the thing we're trying to maximize is the volume of this box. And so in general, the volume of the box is the length times the width times the height. And so what are each of those dimensions going to be? Well, the height is going to be x. So this is equal to, the height is going to be x. Now what are each of the side lengths of the base going to be? So once we cut the corners away, this side length of the base is going to be 12 inches minus 2x. So we're cutting one x away and cutting another x away from the side. And similarly, this is also going to be 12 minus 2x, this side length as well. So this is going to be 12 minus 2x times itself, so squared times x. So that is the length times the width times the height. That's the volume of this box. In this case, all of the equation is only in terms of one variable, so we don't need to use substitution or anything. This is already just one variable, so we're done writing our equation. That's all we need to do. So we're writing an equation that describes what we're trying to maximize or minimize. Volume equals 12 minus 2x squared times x. That is our equation. We now want to find the critical numbers, the potential maxes and mins, using the first derivative. So at this point, we could do two different things. We could either simplify, we could expand this out, and then just use our tools for taking the derivative of a polynomial, or we could use the product rule and the chain rule. Either way is fine. Just for fun, I'm going to use the product and chain rule. So when we take the derivative of this equation for the volume using the product rule, we've got the first 12 minus 2x squared times the derivative of the second. The derivative of x is just 1, plus the second, that's x, times the derivative of the first. So this is using the chain rule, 2 times, leave the inside alone, 12 minus 2x, subtract 1 from the exponent, multiply by the derivative of the inside, that's just negative 2. And so then v prime is, so we'll want to simplify this because eventually we'll want to set this equal to 0 and solve for x. So we've got 12 minus 2x squared plus a negative 2 times 2, so that's minus 4x times 12 minus 2x. So one thing I could do at this point is factor. So I've got a 12 minus 2x in both. And so I could factor out 12 minus 2x. V prime is 12 minus 2x times, it's multiplied by itself, 12 minus 2x, and then in the second term it's multiplied by a negative 4x. So that's how that factors. And I can continue factoring that, or continue simplifying that. V prime is 12 minus 2x times 12 minus 2x minus 4x, that's 12 minus 6x. And so that's a nice factored form of my derivative. To find the critical numbers, I need to set this equal to 0 and solve for x. So I've got two potential critical numbers here. 12 minus 2x, when I solve for x, that would give me x equals 6. And 12 minus 6x, 12 equals 6x, that would give me x equals 2. So I've got two potential critical numbers. Now let's think about each of those critical numbers. So, I've got this sheet of tin, I'm bending up the sides, x is the side length, and 12 minus x is the height, or 12 minus 2x is the height of this box. So what would happen if we've got x equals 6? Then 12 minus 2x would be equal to 12 minus 12, that would be 0. And so this box would have a base of 0 by 0. It would have a volume of 0. So this answer doesn't make sense in context because this would be a base of 0 by 0 for the base, and this would have a volume of 0. We would be not maximizing the volume at all because it would be 0 by 0 by the height, so that would be a volume of 0. So that answer doesn't make sense in context. X equals 2, yeah, both the base and the height would be positive values, so this could be okay. And, if we think about just in context, what are the values that make sense? The sort of domain of this problem would be 0 less than x less than 6. So if x was equal to 0 or less, then we'd have a non-positive height for the box, which again would not be possible. If x is greater than or equal to 6, we have a negative or 0 value for the width of the box. All right, now we want to verify that this potential value, x equals 2 inches, actually does give us, in this case, a maximum for the volume. So we could do this using either the first or second derivative test. Because my first derivative, it's a little, to take the second derivative, I need to use, the product rule or something at this point, the way I've done it. I'm going to use the first derivative test this time. So I'm going to make a number line over the domain from 0 up to 6. And I'm going to test points before 2 and after 6. So I could test 1 and I could test 3 in the derivative in v prime. So v prime of 1, we know that that is 12 minus 2 times 1 times 12 minus 6 times 1. I'm using the derivative and plugging in that value. So that's 12 minus 2, that's a positive number. 12 minus 6, that's also a positive number. That means v prime of 1 is greater than 0. So it's positive here. We're increasing on this side of the value 2. When we take v prime of 3, that's 12 minus 2 times 3. So 12 minus 6 times 12 minus 6 times 3, 12 minus 18. So 12 minus 6, positive, 12 minus 18, negative. So this would be negative. This would be negative in the interval from 2 to 6. And so we are decreasing over this interval. And that tells us that the function is increasing and then decreasing. And it changes at x equals 2. So yes, x equals 2 gives a maximum for the volume. So we have verified that that truly is a max, and now we want to identify all the relevant values asked for in the problem. So now we've got this sheet of tin. We now know that x equals 2 are the side lengths that we're going to fold up to make this box, 2, 2, 2. And then our 12 minus 2x is going to be the base that's left over of this box. So we're folding up this box, and so we were asked for x equals 2 inches is what we want to cut from the sides. So we are going to cut out 2-inch by 2-inch squares. And we were also asked for the volume of this box. And the volume of this box has base 12 minus 2x by 12 minus 2x, so 12 minus 2x squared times x was the volume of this box. So in this case, the volume is 12 minus 2 times, this is 2 inches, minus 12 inches minus 2 times 2 inches times 2 inches. And so this is 12 inches minus 4 inches, 8 inches squared times 2 inches. And so that's giving us 64 times 2, 128 inches cubed is the volume of this box. Here's another example to try. A truck is located 650 miles east of a sports car. The truck is driving west at 60 miles per hour, and the sports car is driving north at 80 miles per hour. When will the car and truck be closest to one another, and what will this distance be? So I encourage you to pause, draw a picture of this, and think about using our process to find this minimum distance. Okay, so we've got a sports car and a truck. Here's my car, and the truck is west of the sports car, so it's over here. So here's my car, or my truck, and there's this distance of 250 miles between them currently. Now the truck is driving the truck is driving west at 60 miles per hour, and the sports car is driving north at 80 miles per hour. So as this car and truck move forward, what's the distance between this car and the truck? So if, this down here is x and this here is y, the vertical and horizontal height between them, then the distance between them is the square root of x squared plus y squared, because we can just use the Pythagorean theorem. The distance squared is going to be equal to x squared plus y squared. The hypotenuse the square of the hypotenuse is equal to the square of each of the sides added together. So we're trying to now minimize this distance, but we also have some other information. We also know that the truck is driving west at 60 miles per hour and the sports car is driving north at 80 miles per hour. So this distance is changing, and we have to think about how this distance is changing at those times. So let's let t be time passed in hours, and let's think about what x and y are at each of those points. So x, the horizontal distance, is 250 miles is the original distance minus the truck is driving 60 miles per hour. So 250 minus 60 times t is the distance, the horizontal distance between the truck and the car, and y, the vertical or the north-south distance between the truck and the car is, it starts at 0 and it's increasing at 80 miles per hour. So it's 80 times t, where t is in miles per hour. So that means that our distance is really the square root of 250 minus 60t squared plus 80t squared. The horizontal distance plus the vertical distance, each of those squared, and then square rooted. So that is the distance, and so that is what we want to minimize. We are trying to minimize the distance between these two vehicles. So we could take our first derivative and go from there, but I'm going to actually make this a little bit easier on ourselves, because this distance is going to be greater than 0, and so minimizing d in this case is going to be the same thing as minimizing d squared. So I'm going to, just to make this an easier derivative to take, I am instead going to minimize the distance squared, minimize d squared equals, getting rid of the square root, 250 minus 60t squared plus 80t squared. I'm going to minimize that, the distance squared, using our first derivative. So now taking the derivative of that, d squared first derivative, I could either multiply out first or I could use the chain rule. Either way is fine. Let's use the chain rule. So 2 times, leave the inside alone, 250 minus 60t to the 1 times the derivative of the inside, that's negative 60, plus the derivative of this next piece. Again, I could multiply out first or I could use the chain rule. So I'm just going to use the chain rule. 2 times 80t, leave the inside alone, to the 1 power, multiply by the derivative of the inside, that's 80. Okay, so let's simplify this now. D squared prime. So we've got 2 times negative 60, negative 120 times 250 minus 60t, plus 2 times 80, 160 times 80t. And so now I just want to continue to simplify. I can distribute and multiply out to simplify that. So when I distribute and multiply out, I get that the derivative of the distance squared is negative 30,000 when I multiply negative 30,000, when I multiply negative 120 times 250 minus a negative, so plus 120 times 60 gives me 7,200 t, plus 160 times 80 gives me 128,000, or 12,800 times t. And so one more simplification, d squared, the derivative, is negative 30,000 plus, that simplifies to 20,000 times t. So now I'm going to set this equal to 0 and solve for t. So setting that equal to 0, solving for t gives me 20,000 times t equals 30,000. And dividing both sides, t is 20,000 over 30,000, or 30,000 over 20,000. And that reduces to 3 over 2, or 1.5. So 1.5 hours is our critical number. And now we need to verify that that really is going to give a minimum for the distance. So we want to verify that t equals 1.5 gives a minimum for the distance squared, and that would also be for d as well, for the actual distance as well. So we see that the first derivative was negative 30,000 plus 20,000 t. So when we take the second derivative, derivative of negative 30,000, just 0. Derivative of 20,000 t is 20,000. And note this is always greater than 0, so this is concave up. So we're using the second derivative test this time. It's concave up, and because this function is concave up, that means that this value, this critical value where the first derivative is 0, is going to be an absolute minimum. And it's an absolute minimum because this function is concave up the entire time. So this really is an absolute minimum. T equals 1.5 minimizes the distance function squared, and therefore also minimizes d. And so that is our minimum. That is the time at which we have a minimum distance. We were also asked what the minimum distance was. So our distance function was the square root of 250 minus 60t squared plus 80 times t squared. That was our distance function. And so that's the square root of 250 minus 60 times 1.5 squared plus 80 times 1.5 squared, that whole quantity squared. And if we simplify that, we'll get a very nice distance of 200, so that's 200 in miles. So the minimum distance between these two vehicles is 200 miles, and this occurs at t equals 1.5 hours. So min distance is 200 miles, and this occurs at t equals 1.5 hours, an hour and a half into both of these vehicles' journey. All right, here is one more example for you to try. An open cylindrical can must hold 1,000 cubic centimeters of water. Find the dimensions that minimize the total amount of metal needed to construct this can. All right, so let's start by drawing this can. So here we go. Here's the can, and it's got an open top. And we know that the volume needed is 1,000 cubic centimeters. And we want to find the dimensions that minimize the amount of metal needed. So we want to minimize the surface area. We want to minimize the surface area. Let's call that SA, surface area. And so what is the surface area of this can? So we know the area of a circle. The area of a circle is pi r squared. What about, so that is like the bottom of this can, and it's an open top, so we don't have to worry about the top. But what about the side? So the sides. Now, if we take this can and kind of imagine cutting it out and rolling it out, then if we cut along the side of this cylinder and just roll it out flat, that's going to have the same surface area. It's just this rectangle once we roll it out flat. And so what dimensions does that have? Well, whatever height the original cylinder has, that's going to be the side length of one of this rectangle. What about the length along this way of this rectangle? Well, that's the circumference of this original cylinder. And remember that the circumference in terms of the radius is 2 pi r. So now this is a rectangle with 2 pi r as one of the side lengths and the height of the cylinder as the other side length. And so that tells us that the surface area for this cylinder is, well, we've got one rectangle with length 2 pi r, height h. So the area of that is just 2 pi r times h. That's the area of the sides of the cylinder, plus the area of the bottom of the cylinder, which is a circle, pi r squared. So we're trying to minimize that, but right now we've got two variables, r and h, and we want just one. So let's use the fact that the volume is 1,000 centimeters cubed, and think about the volume of this cylinder. So the volume of this cylinder is going to be the area of the base, pi r squared, times the height. And anytime you have some kind of solid where you have some constant base, whatever the base is, the volume of that solid, if it's the same throughout, is just going to be whatever the area of the base is times the height of the solid. Okay, so pi r squared h is the volume, and so we could solve, say, for h, volume equals pi r squared h, and we can solve for, and that's equal to 1,000 centimeters cubed. Again, we'll leave off the units until we're done at the end. So solving for h is equal to 1,000 over pi r squared. So that is h, and we can plug that in to the surface area so that we'll have this equation in terms of one variable that we can take the derivative of and solve. So the surface area is 2 pi r times h, 1000 over pi r squared, plus pi r squared. That's our surface area. We can simplify that a little bit. Our surface area is pi cancels with pi. One of the radiuses cancels with one of the radiuses here. So we've got 2000 over r plus pi r squared as our surface area. So to find the critical values, we'll take the first derivative. Before I take the first derivative, I'm just going to rewrite that as 2000 times r to the negative 1 plus pi r squared. And now taking that first derivative, SA prime, the derivative of the surface area, is negative 2000 r to the negative 2 plus derivative of pi r squared. Pi is just a constant, so it stays there. Pi times 2r is the derivative of r squared. I'm going to be setting this equal to 0 and solving for r. And so I can add that 2000r to the negative 2 over to the other side. 2 pi r is equal to 2000 r to the negative 2, 2000 over r squared. To solve for r, I can multiply both sides by r squared, and I've got 2 pi r cubed is equal to 2000, now I can divide both sides by 2 pi, so I've got r cubed is equal to 2000 over 2 pi, or 1000 over pi, and taking the cube root of both sides means that r is equal to the cube root of 1000 over pi. 10 times itself 3 times is 1000, so the cube root of 1000 is 10 over the cube root of pi. And if you throw that into a calculator to get an approximation, you'll get 6.827 as an approximation of that radius. We were asked for the dimensions of this cylinder, so let's also look at the height of this cylinder. We saw above that we've got the height in terms of the radius. The height is equal to 1000 over pi r squared, 1000 over pi r squared. So that's 1000 divided by pi times r, we found to be 10 over this cube root of pi squared. So that's 1000 over pi times 10 squared is 100 over pi cube rooted squared, so pi to the 2/3. And then that simplifies. 1000 over 100 is 10 over pi to the 1 over pi to the 2/3 is pi to the 1/3, or the cube root of pi. So it so happens that the height and the radius are equal, that they're both 10 over the cube root of pi. So we've got this cylinder whose radius is equal to the height. So it's going to look kind of like that. And the height is about 6.827, and the radius is also 6.827. So we've got dimensions. Radius equals 10 over the cube root of pi, and height equals 10 over the cube root of pi.